Hello everyone, this is Felix from GMWolf. Today I want to talk about what integration is, how it's used in video games and how to implement it. Integration is used to calculate the area under a graph. For example, in this velocity time graph, the area represents the distance the object has moved. Velocity times time equals distance. This can also be used with an acceleration time graph. This will yield a value for velocity. This is especially useful as you can then further integrate this value to obtain the displacement. In fact, this is how you can calculate the trajectories of objects. You calculate the acceleration and then get the position of the object at any given time. Some of you may already have seen integration at school. In that case, you have learned to use calculus in order to calculate the derivatives, and this may be putting you off looking into integration in programming. Luckily for us, we have numerical methods to integrate functions. There are many advantages to using such methods. They are much easier to implement with code. As I've already said, you have probably already been using it, maybe without even realizing it. They also allow to integrate methods which otherwise would not be possible to get solutions to. And finally, they are very lightweight. You can use these methods on hundreds of different objects without it having any significant impact on performance. However, they can be quite inaccurate compared to actually calculating the integrals. So the method I'll explain today is called Euler integration. It is the simplest form of numerical integration, but it can be quite inaccurate. However, the method is more than good enough for the large majority of your games, and the accuracy can be improved at the cost of some extra CPU time. As I mentioned before, Euler integration is very simple. Let's have a look at how you would integrate the acceleration of an object to obtain its position. This method requires that we start with a value for its x position and a dt variable which represents the time step we are taking. So let's go into our object here and add a position variable, which I'm going to call s. And I'm going to set it to 0. Next, we need to figure out a dt variable. Now, the dt variable is actually the difference in time, so the time between the different steps we're taking. In this instance, we're going to be using a variable called delta time, which GameMaker already calculates for us, which will allow us to very quickly and easily calculate this time between different steps. So we're going to leave this, so we're just going to set tt to 0 for now. Now, in our program, we also need to figure out the acceleration of the object in order to integrate it. And for now, we're going to set it to a static value that won't change. So I'm going to set the acceleration to 5. Alright, so that is the first step of integrating something. It is to have its original value. So we can now go into the step event, and this is where we'll step through each of our integration steps in order to calculate and update the position of our object. So what we have to do is to, well, first of all, figure out what dt is. So I'm going to say dt is equal to delta underscore time. Now delta time is in microseconds, and so you have to divide it by 1 million in order to get it in seconds, which is what we want. So now that we have our dt value, we can multiply it by our acceleration, like so, in order to obtain the difference in velocity. So dv equals to acceleration times dt. We can now add our difference in velocity to our existing velocity, so v equals v plus is equal to dv. And after that, we can do the same thing for our velocity. So we have another value for velocity, so we can do velocity, so we can do difference in displacement, so ds is going to be equal to our velocity times difference in time, and then we can simply add the difference in displacement to our displacements. And that's basically it. So let's go back into our create event and initialize variables we haven't done so already. So dv, v, and ds. dv is equal to 0, v is equal to 0, ds is equal to 0, and it is all good. So what we can do now is go into the draw event and add a quick bit of code in order to see our results. So I'm just going to draw a circle at position S, 10, with a radius of 10, and no outline. Actually, I'm going to lower this to 100, so it's nice in the center of the room. Open up a room and add our object. What we should see is an object accelerating to the right using numerical integration. And as you can see, we now have a black circle moving to the right at an increasing speed. In fact, it is accelerating by 5 pixels per second, which is perfect. So let's close this now and look at, well, how accurate this technique is. To do this, I'm going to write a quick bit of code which will calculate the actual position it should be at. So I'm going to call this AS is equal to, and it just so happens to be 0.5 times our acceleration times the current time we're at squared. Now we don't actually have the current time yet, so I'm just going to do t plus is equal to dt, and I'm going to go back into my create event and say that t is equal to 0. So this part here you don't really need to understand, but basically speaking it is the proper solution to finding the position of an object accelerating at a constant rate. And if I press, if I go into the draw event, copy what we already have, and have the same circle be drawn 100 pixels below, but this time using the actual displacement, which I called AS, like so, what we should see is two objects moving at about the same speed. So as you can see, both circles seem to be pretty well in line with each other. However, if we wait a bit, we'll see that this circle will start getting will start being ahead of that circle. Now I don't know if it's very visible in the video, but you can very slightly see that one of the two circles is indeed going faster, slightly faster than the other. However, it is pretty good. It's very hard to see the difference, and for most of your games, this is perfect. Now let's have a look at what happens when we lower the number of steps we have. For example, right now we were going at 200 steps a second. That's pretty fast. Let's lower this down to, say, 5. Now we should see a much bigger difference in our two integrations. So of course we see everything running at 5 frames per second, which is what I set it to. However, near the end we should see that one of the two circles should be ahead of the other, simply because we're being less accurate. Here you go, we can start seeing that the top circle is slightly ahead of the bottom circle. In fact, we could probably see this better if I were to, say, change this value to be 10 times smaller, 10 times larger, sorry. And we should see a much bigger difference this time. Yes, now we can, it goes past much faster, but we could definitely see a bigger difference in the two. So the number of steps in your simulation is very important. Now most of you will keep it to 30. So let's see how that looks like. Having an FPS of 30 should give us pretty good looking results. Again, we're back at a nice and smooth simulation, and we really can't see much of a difference between the two circles. So between the actual integration and the numerical integration. As you can see, there's a very small difference, but it's very noticeable. So for a very simple simulation like that, everything seems to work very nicely. Now, although this was a very good approximation, you may sometimes want to make it more accurate. To do this, what you can do is have the use of substeps. So what we would do before is simply increase this room speed over here. However, this is not necessarily what you want to do. So in order to increase substeps, what we have to do is repeat this step 3 times. So what we can do is right over here, press, for example, repeat, and the number of substeps we want to do. So if, say we want to have 10 substeps, we go like so. We make a new variable called var and called sub. Let's make it 10. Repeat sub. All of this right here. Let's indent the code to make it nice and readable, like so. However, now we're timesing it by dt, and that's not quite correct. What we need to do is times it by corrected dt. So we're going to call it sub delta time, and that's going to be equal to dt divided by sub. Now all we have to do is do sdt, sdt, sdt. Now if we press play, we should see the exact same thing happening. However, this time we're going to have a much more accurate simulation. So we should see almost no difference, because now we're running at almost 300 steps per second. And yes, we don't see much of a difference at all, which is absolutely great. Even if we were to quit this, we could increase the substep to 100 and decrease over here the speed to 1, and we should see virtually no difference between the two. Again, because it will be the equivalent of running 100 steps a second. So as you can see, it's only updating once a second, which is incredibly slow. However, we don't see a single difference between the two. So this is how you implement substeps, which is very important if you want to have an accurate simulation. Right now we're using quite a simple model with only one set of values that need to be updated, etc. However, if you are to create a system where you have, for example, planets that attract spaceships, etc., you'll want to have a very accurate simulation for it not to start being completely unstable, and the way you do that is simply by increasing the number of substeps. So this is basically it for this episode on numerical integration. As you can see, there's not much new that you haven't seen. I can show you how you can actually simplify this code into something that will look a lot more to what you would normally have used. So you would simply go s plus is equal to over here, take this away, and then v plus is equal to like so, and take this away, and all of a sudden this part here, which I'm going to put between two commented lines, like so, looks a lot more like what you may have used before, with the exception of this times sdt. And this is perfectly normal. This is, the most used method to calculate, the position of an object. However, most people often forget to times it by the delta time. And so this is why I'm making this video, is to show you the proper use of numerical integration. So yes, if you like this video, please leave a like, and if you want to see more, please subscribe. It will really help. If you still have questions about things, how to implement different types of integration in your projects, please ask in the comments below, and I will make sure to answer your question either through the comments section, or I may even make an entire video depending on how in-depth your question is, and if other people are asking the same kinds of questions. And apart from that, I guess I'll see you guys next time.